Yes, thank you very much for coming. And I also complain a lot because I kind of, in this period in particular, I struggle in trying to understand what it means to do something relevant as opposed to something incremental in this period of fast evolution of AI science. It's a very difficult moment in this respect. There's a mess of an incredible number of papers, a rhythm dictated by conferences, which somehow doesn't resonate, in my opinion, with trying to do something which is really kind of innovative and requires a lot of time. So I struggle at this tension that always worries me. And I know that for young people, it sounds kind of necessary to follow the mainstream. However, I do believe that if you want to do something, it's more important one relevant thing in your life than 100 medium level kind of results. And that requires a lot of time. So I don't know, it's your problem to solve. But I'm struggling. So I'm saying this because I've been working on this problem for 4 years without publishing anything. And so that's why I try to justify. So I'm going to do something very basic. And namely, I want to find kind of an alternative way of doing learning in deep networks or at large. So what I'm going to do, and please, let's talk about it. Whatever you want to say, let's just discuss. For me, it's very interesting if you do it like that. So I'll just briefly remind you about physical learning processes. Then I want to remind you some known results about the dynamical behavior of asymmetric recurrent networks. Asymmetric comes from the fact that you don't have an energy function, you don't have a Lyapunov function. So it's more realistic in a sense with respect to neuroscience at least. And then I want to talk about the fact that in this network, if you tune a little bit the parameters, a set of fixed point emerges, which is connected in large scale. We call it the representation manifold. And this allows the dynamics to converge and also to implement learning. So and this can be implemented on an arbitrary architecture, even multi-layer without difficulty. So that's this, and you have zero gradient in the sense they don't use it, not that the gradient is zero. Okay, so just to be blunt in a sense, so deep learning in a nutshell, you have a complicated network, you have a loss function. I'm sure I don't need to say these things. We use gradient backpropagation, and it's a first order method that designed for complex problems, and magically it works. And I just want to say that there's nothing magic about backpropagation. It works because the landscape is not that hard to optimize. And so many other algorithms should work. So that's my main argument. We have some evidence for that, at least for classification problems. And so that's this is the reason why I want to just remind you that the learning problem, of course, not for pathological data, for typical data, is not that hard. So do we really need other models for machine learning for AI? Well, certainly the current models, like say transformers, have almost nothing to do with any biological or even hardware circuit. So the one point I want to make is modern AI through backpropagation is an intrinsically software method. You cannot implement it. You can only simulate it. So there's no way of getting your gradients around your device. So this is little to do not only with biology, but also with hardware. So it's an intrinsically software theory. And as a physicist, I kind of feel unhappy about this. And maybe, by looking to something different, we also can discover different principles for computing. Now, so this is kind of clear why belief propagation is not, sorry, not belief propagation. Backpropagation is not of interest for biology. They consume a lot of energy. This is a well-known problem. And, it's also unclear whether this kind of system can continue to evolve. I mean, is it going to saturate at a certain point? Do we need different models? This is still under debate, right? Because whether, say, language model plus computed inference time is going to continue to grow in performance is kind of unclear, right? So maybe we need something else. So what I want to talk about is, can a physical system perform complex learning, so potentially in a multi-layer network, avoiding the propagation of gradients? That's my objective. Okay, so first of all, of course, not the first one to answer this ask this question. There are many methods, many attempts to perform the same task. So, for instance, there are techniques that, through a distributed computation, try to approximate the gradient. So, target propagation, feedback alignment, equilibrium propagation, maybe you're more familiar with. I will say a few words about it. Then there are other methods that do not try to approximate it. So these are methods that essentially try to do what we are doing through backpropagation through a distributed computation. Here we have other technique like predictive coding, which is very much used in neuroscience, plus other algorithms. They do not try to approximate the gradient. They use a different principle. Then there are some biologically inspired techniques like reservoir computing, which is essentially exploits the rich chaotic behavior of asymmetric network to do some signal processing. I'm not a super expert, but and then various algorithms, and in particular spiking neural networks are also used. And you know very well that with spiking neural network, there's a difficulty in learning because you have to do back propagation through time in a spiking network. Come on, it's not going to work, right? I mean, it's hard to believe that it's going to work. So for instance, in a reservoir computing, you have an input, you have a recurrent layer which is chaotic, and then you have a linear output, and the only trained part of the system is the last layer, and they use this, they kind of control the dynamics in order to do some signal processing. I mean, I don't want to invest time on this. I just want to show you the building blocks. Okay, it's not the topic of the talk. Then there's another, in predictive coding, again, neurons are expected to predict what is happening in the next layer. And in order to implement this, you need to have two types of neurons, the typical one plus an error unit that sends back the signal. So this is considered to be of interest for neuroscience. Still, it's a bit complicated. You have to add extra units and so on. I think that maybe the most successful, or at least the simplest to explain approach is equilibrium propagation. Is one of the attempts to do learning without gradients. And this is nothing but the Hopfield model, even reinvented for. Essentially, one takes an energy function. So one has a recurrent network plus a readout layer and an input layer. And for the recurrent network, one assumes that the Wij, the couplings, are symmetric. So one can construct a Lyapunov function, rho of S. So rho of S is the input field of the neurons, and rho of S is just the activation function. Okay, but again, it's not that important. You recognize that this is a Hopfield type of energy function, and so this function is going to decrease with the dynamics, along the dynamics, right? So either continuous time or discrete time. So somehow you can imagine that this is a model that has a lot of fixed points that corresponds to local minima of this function. Okay, and this is this is the Hopfield model essentially, and this has been used by various by these guys, Chelier and Benjo. This is a PhD student and Benjo. And what they do is just they send a signal here, they let it converge, then they send a second signal in which they modify a little bit the cost. They add a cost function to the energy function that somehow tends to polarize the output towards the desired output. And then based on the difference between these two signals, they update the weights in a symmetric way, such that you preserve symmetry and you perform learning. Sorry, I don't really want to invest much time, but essentially you have to think you have a system that has a minima that is going to converge for sure. And then you first make a converge, and you make a converge with some perturbation on the output that has to be big, small in order to mimic a gradient. And then based on the difference between the signals, you update your weights. So it's just, yeah, mimicking the signal plus this condition of having a lot of local minima. I hope it is enough for our discussion. So it's fine. It has some problems. One is apparently, again, I didn't simulate it, but slow training time due to convergence. I mean, this is a well-known problem also of the Hopfield model that is slow at converging. It is sensitive to noise because having a lot of minima, it's kind of a problem, right? Because you plug in a minimum, you perturb the input a little bit, and you end up in another minimum. So this is not necessarily not always useful. And so somehow there's a lack of connectivity in the internal representation of this system. So the equilibrium states always are minimum. Of course, you can have, if you train it long enough, you can induce flat direction saddles and you can move, but it's not the natural setup for this kind of system. Okay, so our approach is, let's take a comparison with this. So in our approach, we have some differences. First of all, we don't care about symmetry. No symmetry at all, so no energy function at all. Second, our signals are non-perturbative. So we are not going to input and output signal that is small because we want to estimate a tiny difference to simulate a gradient. Okay, so non-perturbative. And then it builds on the fact that on the onset of this internal representation manifold in the recurrent part of the network, that is a manifold of connected fixed points that appear in this kind of models. Okay, please ask me if the whatever. Okay, so let me remind you a few things about asymmetric network. Here we are again in the same period of a Hopfield model. So there was a very famous paper by Sompolinsky, Crisanti, and Sommers in '88, in which they studied a recurrent network in which, let's say, the couplings, here I call them JIJ because I use the physics convention about couplings, but these are the W's, okay? And they are totally factorized, namely the fact that these neurons interact with these neurons is independent on the fact that there exists an opposite complementary, say, connection. So everything is factorized and independent. Now, if you take this network and you just simulate the dynamics, here is the simplest version in discrete time, in discrete states. But you can, instead of taking the sine function for the neurons, you can take an arbitrary nonlinearity, okay? And write a differential equation in continuous time. What happens for this network is that essentially it's chaotic. When you have there's been some, and this is at the root of this reservoir computing type of networks and also spiking networks. And the problem is that controlling a chaotic system is very, very complicated, in particular if you want to use it for classification, for instance, for some typical AI objective. There's been some work also more recent work by Stern, Sompolinsky, and Abbott, in which they consider a more sophisticated model in which you have also, beside this, this is the nonlinearity, is a hyperbolic tangent instead of the sine, but it's the same thing. So they also consider a self-interaction term, which helps convergence. But somehow in this paper, they missed the key ingredient, and I will tell you about it later on. Okay, so, but since this paper, there's been, thousands of papers about chaos in neural networks. So it's very, very influential. Now, what we are doing now is we are considering a slightly different model. Now, this seems an innocent kind of change, but it is not, and it has an origin that I will tell you in a minute. So we consider a model in which we start to plug in some self-interaction. So this is J diagonal. So it's like a JII, right? So this is a term in which it's a local feedback. So you see, you have a neuron that somehow interact with itself. Okay? Again, it's totally asymmetric, the network. I take a random Gaussian, whatever, random couplings, totally asymmetric. And I would like to understand what happens to these dynamics as we change the self-interaction. So I can think to this as an optimization problem in which I just want to know if there exist fixed points of this equation. So it's totally equivalent to ask whether there exists configuration S such that this cost function equals 0, right? Because each term, this is a sum of all the nodes in the network. And for each node, if Si is equal to the sign of the incoming signal, it means that you are in a fixed point, you add a 0. Otherwise, you add a 1. So this counts how many neurons do not satisfy the fixed point condition, okay? So that why did we start here, and what has motivated all this? Well, there is a similarity with learning problems. This is a very famous problem that you know as binary single index model. It makes me laugh because this is a binary perceptron, but now you don't know what a perceptron is, so I have to call it binary single index model. And what is this binary single index model? You have just a single neuron with binary weights, and you want to store some pattern psi. So you plug in your patterns, and you want to find a W such that sigma psi mu is mapped on an output, which is sigma mu. And you have a training set made of all these pairs, sigma and psi. Okay, it's just a perceptron problem, right? And you see that if you compare this problem to the fixed point condition in the asymmetric network, you see it's pretty similar. You have, instead of the label, you have the state of the neuron, then you have a sign, and then the patterns play the role of the couplings. And the patterns are just random. For instance, in the model that we study are just random variables, uncorrelated. So they are uncorrelated, so it means asymmetric network. And SI plays the role of the W. So it's just kind of the dual version of that. And for this problem, sorry, I don't know what okay, there is a difference that here in the binary perceptron problem, single index model, there is a critical number of patterns below above which we cannot store patterns, and this value is 0.83. So it's below 1. But here, the number of constraints is fixed to n, because we have n neurons. We want all of them to be in a fixed point. So that we cannot reduce this number in order to satisfy the constraints. So the only way we can do it is by relaxing a little bit this equation by adding this, for instance, this self-interaction term. There are other ways of doing this. I will mention briefly later. So this is not the only way, but this is the simplest. Okay, and for the binary perceptron problem, it's very well known that there is this, as you change the parameters in the model, at a certain point, you observe the onset of a connected region of solution. There's mode connectivity in the language of deep learning. So there are a lot of configurations that satisfy all the patterns in the learning problem, a lot of configuration of the W such that all the patterns are classified, and these configurations are connected through an extensive region. Notice that the majority of the solutions are point-like. So what is dominating from the point of view of the Gibbs measure are these little dots here that are by far exponentially more numerous than those contained in the connected region. But as we will see, only those belonging to the connected region can be reached by algorithms. So this is the relevant part. And so somehow what we were wondering is that, okay, what about in the dynamics? Do we have something similar in the dynamical behavior of nonlinear devices? Okay, and that was the motivation. So we started by studying this problem as a function of JD and ask what is, how are the fixed points characterized? What is their geometry and so on? Okay, and good. So we do this, and first of all, you can compute what is the typical number of fixed points just by averaging over the JIJs. And you can do this by first moment method, which turns out to be exact. If you do the second moment, you find the square of the first. And you find that the log of the number of fixed points as a function of the self-interaction follows this curve. What does this mean is that if the self-interaction is 0, you have, this is the 1 over n log of the number, right? Because we expect to have an exponential number of fixed points. Now, if your self-interaction is 0, you have 0 fixed points. And if the self-interaction goes to infinity, all configurations are fixed points, right? Because, well, where is the equation? Yeah, sorry. Of course, if JD is big, you can neglect this part, and everything is a fixed point. Okay, so good. Now, if you do a more sophisticated calculation using replicas, and you try to analyze the geometry, you discover that these points that are counted by this first order method, which are the dominating ones, so the result is correct up to exponential order, turn out to be isolated. This is the scenario. So this is a problem. Due to the, let's say that, let's assume for a moment that this is the scenario. Now there is okay, these are results that were known in physics since many, many years, but now have been made rigorous by the so-called overlap gap property result. If this would be the final situation, there would be no way in the large n limit to actually find these fixed points by any sort of stable algorithm, okay? So in particular, the physical dynamics is not going to reach them. Okay, so this, just let me remind you what the overlap gap property says. If you have an optimization problem, and with this picture, I just draw the optimal configuration of your optimization problem. If the optimization problem is not like this, where you have wide minima, but you have only tiny minima that are isolated, namely the distance, the internal size of the minima, it's much smaller than the distance between different minima. This is a technical condition for large dimensionality. Then a stable algorithm is not going to find this solution in sub-exponential time. Okay? So going back to this scenario, this would kind of tell me that there's no hope of making this network converge, which is pretty consistent with the chaotic behavior, right? Good. So, but if you now simulate this network, and you see that, okay, for small j, if in fact you only observe chaotic behavior, but at a certain point, then the dynamics starts to converge. So what's going on here? Well, it means that there must be something which is does not satisfy the condition of the overlap gap property. Namely, you need to have a wide region of solution of optimal configuration. And this is, was expected from the result on learning that I mentioned due to the analogy. But okay, let's forget about that. It means that you need to have these kind of rare regions. Rare, why? Because when you do the first order calculation, which is exact, let me remind you that these are the dominating ones, not the dense region. But there must exist some dense region that violate the overlap gap property, and that's it. So this is what we are looking for, to understand what happens in these networks, okay? So we ask ourselves, does it exist a region somewhere in the configuration space of the network that is particularly dense in solution, such that the theorem doesn't apply? And okay, this is an old result, 10 years old result. There's a technique to do this, which is called the local entropy method. What we do essentially is to look at the optimization problems rather than point-wise by trying to optimize the center of an hypersphere of radius d and use as a cost function the number of solutions contained inside this hypersphere. So we want to find if there exists a configuration S tilde, which is surrounded by a very large number of other optimal configurations. Even though the total number of configurations, which is exponential, is still much smaller than the total number of other configurations, okay? So it's a way of looking to rare events. So this is called the local entropy method. And clearly you see that if the situation is such that only isolated solution exists, for this sufficiently small, this number of configuration inside the hypersphere would be just 1. So this would give you 0. So this would be totally useless, right? And so this kind of cost function is going to focus only on these dense regions. And luckily enough, you can do calculations with that. So again, we are looking at this type of minima as compared to that type of minima. And Okay, so there are two quantities that I can estimate. One is the number of such regions, how many regions of radius d exist that have a certain internal entropy. So I call it a log of the number of optimal configuration inside the sphere. I call it internal entropy. So there are two quantities we can compute. So one is the external entropy, namely how many regions do you have that have a certain given internal entropy. So SI and SE. This can be computed just by standard thermodynamic. Okay, that can be computed. I don't know if you're a computer scientist or physicist, whatever. It doesn't matter. You can compute them. Again, the larger limit and having averaged over the couplings. Okay, so these are the expected, most probable values. Okay, so we can compute these quantities. Okay, and we proceed as follows. This is expression. It doesn't matter what it means. I don't think it's very important, but we can compute the value of this internal entropy and the external entropy as a function of the radius of this hypersphere and y, which is a conjugate parameter to this cost function that counts, which is proportional to the internal entropy. Okay, it's the log of the internal entropy. Sorry, is the internal entropy. So the larger is y, the larger will be the internal entropy. Namely, if we take y large, we are going to focus on regions that have a lot of solution inside. Okay, so we use y to control this aspect. Now, what is the problem? If y grows too much, it may happen that the cluster, they disappear. So you have two entropy. Remember, one is the number of clusters, and another is the internal entropy of the cluster. So maybe they disappear. So solving this equation is a bit complicated. So for each distance, you have to find y such that the external entropy vanishes. So it's the limit case in which you are left just with one giant cluster of high internal entropy, and then you solve the saddle point equation that come out, and you compute the internal entropy. And then so for each value of d, you have to do all this complex procedure of search and solution. But okay, this is a technicality that is of interest only for if you're working in statistical physics, probably. But this is what comes out, is that, okay, these are different values of the self-coupling, okay? This is the distance from some optimal centroid or the hypersphere. And you see that if the self-coupling is very small, the internal entropy is always negative, which means that there are no solutions inside. There's only one solution. And so if J is small, for small distances, these are isolated. These clusters do not exist. However, as you increase J, at a certain point, this curve changes concavity, and this is where an extended region appears. So the value of J such that this curve, the second derivative of the curve, changes sign, so more or less the yellow curve, identifies the critical value of J such that you can, as you increase the radius of the hypersphere, you continue to see more and more solution. Whereas below this value, these curves are kind of going down, right? So it means that there is the solutions are concentrated in a certain region, and then they decrease. And also, I mean, I should zoom here, but there's some numerical problem. This curve always go like this. You know, it's they have to go to zero from above, but it's a technicality. Just to say that if J is small, all the solutions are concentrated, and if J is sufficiently big, then you have an extended region all of a sudden. Which means, going back to our scenario, is that in fact, if this is the whole configuration space, you really have a cluster which has a very strange shape, but which is very wide. Okay. Now, so this is the phase diagram we find. Maybe I go directly to this picture. So for J small, we have either isolated fixed point or very, very tiny clusters. I mean, if you look at the size of these clusters, it's very, very close to zero. I mean, they're very tiny, okay? If you're interested, I can tell you about the details, but these are really, imagine the cost function, these are really minima that are very, very narrow, okay? But then, as we go above this value, you know, what we call an accessible dense region of solution appears. And we call this, for reason, we call it the representation manifold, but we will see. So this is an analytic result. which is consistent with the fact that there are many algorithms. Let me see if I, no, sorry. There are many, depending on which algorithm you use to find this fixed point, you have different critical values that are algorithmic dependent, but this is a kind of a necessary condition in order to achieve convergence, because otherwise essentially the overlap gap property would forbid any algorithm to converge. Is it too, I know it's far from AI, but then we go to learning, and, yes.
So we can ask questions.
Yeah, sure.
You did not talk about the stability of the fixed points, but we know that on the extreme left here, there are many unstable fixed points. At some point, some fixed points or some clusters should become stable.
Yeah.
And how do you know this happens?
First of all, this is a discrete system; it's not a continuous system. So we have to talk about what it means, stability.
Yeah.
Okay. So, but
I was thinking of continuously valued.
The point is that let me put it like this in a very intuitive way. If you have a region of connected minima, and you flip one of the variables, you're going to end up in another one nearby, so it's stable.
Yeah.
Okay, that's the intuition. But if you ask me about, did you solve the dynamical equation for this problem? No, we didn't. So if you want, we didn't have time to do that. It's certainly worth doing it, but we didn't have time. So, whereas in the continuous case, the discussion is more complicated, but maybe later, because I really want to go to the learning part. Okay, good. Now, this kind of scenario can be extended to multi-layer networks. Now, in multi-layer network, we call it multi-layer chain model. You can imagine to have modules that are just like the previous one. And now you put a positive interaction between neurons in different, so this is a sparse interaction. So neuron number one in this module interacts only with neuron number one in the second module, and so on. So you have order n here interaction, whereas inside you have order n squared. And if you think about it, the diagonal term is just the analog of this one when you have just one model, right? And what I think is kind of nice about this, so let me anticipate, we can solve analytically also this problem without learning for the moment. And we can show that even if you set the third coupling to 0, just by playing with this interaction, you can induce the onset of this connected manifold that allows algorithm to converge. This is non-trivial, okay? So, because these are different networks with different realization of the couplings. And if you force them through some positive couplings to be correlated, this produces fixed points that belong to these connected regions. Okay? And this is kind of non-trivial. Well, just to mention, one can do again, play the same game as before. You can count the number of solutions. The first moment is still exact, and then you can compute the local entropy. It's very complicated. It took, I think, 4 months to produce these curves. And here you see the final result. So the green line is just the model, just the core model I discussed with you before. So the green lines you see, if the diagonal term is below 0, 1, you have this behavior of the curve. And if it is above 0.1, it changes concavity. So for the core model, a critical value between 0.07 and 0.1 identifies the onset of disconnected regions and the fact that you have an entropy that grows as the distance grows. Now let's look directly to the orange curve. You can set the diagonal term to 0 and just play with the connection between modules. And again, you see that if the value of this connection is below 0.4, then you have this kind of concavity, which means that if you look at this curve, they have a maximum, and then the rest of the curve violates certain geometrical bounds. So it's kind of incorrect here, but correct in the first part. It means that you have just isolated solution. Sorry for being a bit fast. If you want, we can go back to this. But there exists a critical value of the coupling between modules above which all this network converge, and they have these joint connected regions of fixed points. Kind of nice, because you see, you initialize the system, you let it converge, and it means that this neuron here is correlated to that neuron there. Everything becomes correlated and rapidly convergent.
Just to clarify, because you said it probably at some point, but I missed it. The JD is the diagonal, and
Yes.
the non-diagonal part is chosen how? It's fixed random or?
No, it's fixed. It's just a coupling, a ferromagn, a positive coupling. It's like you're forcing this module to have a certain overlap.
So even within the layers, I thought this was like
No, within the layers are totally random and independent.
okay, random.
So these are different core modules, and you just force them to interact, to behave in a sense a bit in a similar manner, even though they are different, right? So you force correlation.
The spins, not the interactions.
The interaction are quenched and random in different module by module. Okay, so there are many dynamics, and let me go. So now let's go towards learning. Let me just tell you why we call it internal representation. Because if you take, let's say, okay, let me go here. Okay, let's say that you have one module and you force through some external signal, you send a signal to all the neurons, and then you make it converge. Then the state at which the network converges, we call it the internal representation of the external signal. Okay, so maybe it's easier just to look at the update equation. Oops, sorry. You see, this would be the normal equation. You add an external, sorry for this, this is another lambda, sorry, I apologize for that. You inject another signal and you update this equation and they reach a fixed point, eta, and we say that eta is the internal representation of psi. Okay, and this internal representation belongs to this connected manifold. Kind of interesting, right? So you have so any input you can give is going to converge. At least this is a numerical observation, and it's going to converge in this connected manifold. And one can look at how this connected manifold looks like. You find you take two different signals, and then you make it converge, and then try to interpolate between the two. And you find that depending on how you interpolate, you can find different paths connecting two internal representations. And this is the overlap along the path. And you see that it's kind of a hierarchical structure. I mean, it's kind of interesting. This is just a numerical result. So I don't want to spend too much time because I don't even know what time is it. Well, yeah, I better move. So how to implement learning? And this is the new part. Well, again, let's take this model. So many modules, lambda, and neurons, as I told you, if lambda is big enough or JD is big enough, all the neurons are correlated at convergence, right? Because for the very simple reason that if you cut this interaction, the system is chaotic. If you put the interaction, so you put it in correlation, then it converges. So the first experiment, this is, the day after I resigned from being head of department, I did this experiment. That was kind of, and so what I did is that I forced the system, I took a multi-layer network, I forced the system, the first layer to be, say, all plus. I plugged in an external signal with all the neurons receiving a positive signal. And then in output, I put a signal forcing all the neurons to be in the down direction, -1 direction. And then I observed the dynamics as a function of this lambda, and I found that the internal layers just rotate. Okay, which means that essentially this is a system that can implement any kind of hetero association. Okay, I could change its vector as I wanted, and you still find something like that. So this is a very simple device that can implement any input-output relation. And this is what we are going to exploit. So let's consider learning now for the simplest version. We can do it in multi-layer, but it's just more complicated. So let's consider just one single module with some JD, some diagonal interaction terms. So we have an input layer, some W in connections. We have the J inside, and then we have some W out that connect the state of the network to some readout layer. I mean, this is a pretty standard architecture, right? And what we can do is the following. We can plug in an X and a Y. So imagine that Y is the one-hot encoding, and imagine that here you have images. And let's say MNIST, okay? Here you plug in the pixel of MNIST, and here you have the one-hot encoding of the digits. And so you have fields that project here. This has a different arbitrary size, so we can expand, reduce, we can do a lot of stuff. And what we can do is that we can make the system converge, right? And once we converge, we can try to stabilize the, we can modify both the input layer, the output layer, and the internal layer in such a way that they're able to reproduce the correct output when only the input is given. Okay, so how do we proceed? We proceed that I propose you two algorithms. Okay, we first converge with for each pattern. We first converge with input and output, and we reach a fixed point that we call S star. Okay.
What's the W back? You didn't tell us. What?
This, the blue one. Yeah.
The red one is W out.
Yes, and this is W back. Yes, sorry.
Oh.
Well, there are many choices, but we typically keep fixed W back and just train W out. But
I see. And W in will be trained and J.
Yes. No, J is trained. No, the whole point is about training J. Because that's the difference with respect to, say, the other models. Okay, so let's say that we give this external signal and we converge, right? At this point, since we want to train the network, but we want the network to be capable of reproducing the output in absence of the label, right? So we use the label to find the fixed point, but then when we do learning, we have to take away the contribution from the label, because otherwise, I mean, when you use it at inference, you cannot use the label to predict the label, right? So what we do is that we look at all the activations or local fields that on the single neurons, and we delete by hand all the contribution coming from the right. So we cherry pick, we just delete by hand all the contribution coming from the right. And then with this pre-activation, we just apply a perceptron rule, a local rule. So if the product of the pre-activation times the state is below a certain margin, then we reinforce the JJ. But so this is just, each neuron is reinforcing itself based on its state. It doesn't use any other information. It's totally local. Okay, is that clear? So you see no gradients, zero gradients. And also this operation which we delete is not a perturbative type of operation. Okay, so this is one possibility which works. It was the first attempt, but now we want to do something more reasonable. And we do the following. First, again, we converge with the input and the output signal. But then what we do is just switch off the output signal and reconverge again. Okay? So we reconverge again and we converge to another fixed point. We first reach S star because we are on this manifold. And then we switch off the contribution from the right and we reconverge and we go to S star star. The reactivation or local fields from H star become H star star. And then we just apply a perceptron rule with these new states. It turns out that due to the geometrical shape of this manifold, S star and S star star are practically the same. So the system doesn't move. I use this analogy. Suppose that this manifold is like your hand in high dimension, and you first converge in one of your fingers, okay? And then you remove part of the signal, but you're trapped there. Okay, that's kind of the analogy. And you have an exponential number of fingers. Okay. So it's not, it's horrible, but it doesn't matter. So this is the idea. So you start with an input signal, an output signal, you converge, you switch it off, and you remain essentially there. At this point, you can apply the stabilization of each neuron. And, you know, and here is the accuracy on a certain benchmark that I'll describe in a minute. I just want to show you that this system works only if the diagonal term is big enough, namely only if there is this manifold. Okay. Now, how do we test this? We should have done more serious tests, but okay. We take MNIST, which of course is not a benchmark for anything, but we go from 784 dimensions to we project it in 100 dimensions through a random projector, and then we binarize it. So we take first a compression, then a nonlinear transformation. And this, why do we do this? Because it's smaller, faster, and because linear classifier behave badly on this. So it becomes not really hard to separate linearly. Okay, so it is a benchmark at least for linear classifier. Okay. So, okay, this I can skip. So this is the behavior. So these are the green and the orange are models in which we do not update the JIJs inside the module. And, you know, if you take the system big enough, just by training the input and output layer, you may reach at a certain point good accuracy in training the system, just like you would do with a super vector machine, right? You just expand big enough and then classify, and it's going to work. But you see that there remains a gap in terms of generalization. The blue one is the one in which we also train the JIJs. So the scope of the simulation is just to show that these internal representations are actually useful for generalization. Okay, that's the idea. Okay, this is a little movie. These are 10 patterns belonging to say these are 10 examples from the class 0, 10 examples from class 1, and so on. And we look at the overlap of the internal representation. So how the 0 overlap with the 1, with the 0, with the 1, with the 2, and so on, as learning goes on. And so this is about the internal representation, right? So you see that as training goes on, the system is capable of clustering things that then are easy to classify by the readout layer. Okay. Yeah, I think I can wrap up.
What's the J matrix on the previous?
Sorry?
That's the J. That's which matrix?
So these are we have 300 internal representation corresponding to 300 different inputs after learning. And these inputs are 10 from the class 0. This is MNIST, right? From the digit 0, 10 from the digit 1, 10 from the digit 2, and so on. So you plug in that, let it converge, and memorize the internal representation. And then you do the matrix overlap of this internal representation. So this square is going to measure how much the internal representation of the 0 looks look alike. Okay. And so this is as learning goes on, you see that the internal representation become richer and richer, and they're able to separate. Of course, you still have problem because 0, 1, 2, 3, 3, and 5 are kind of hard to discriminate, right? Even though here we have this nonlinear transformation, compression, so on, but they're still hard. But other things that are, to me seem pretty interesting is that, first of all, it's very, very fast at converging. Learning is very, very fast. So very, very few epochs are needed to train the system, at least for this task. And another interesting aspect is that the fraction of neurons that are actually updated along learning is small, is 2%, which means that this is, from the energetic perspective, is really energy preserving. As this is at the beginning, you have to update, say, 10% of the neuron, but very quickly you go down to very few neurons and you adjust. Of course, this depends on the data. It's just, for this. Another thing which is kind of interesting is the following. Suppose I initialize my system in a fully asymmetric way, or in a fully symmetric way. So I could initialize my JIJs in a symmetric way. So this is a measure of the symmetricity of the JIJ matrix, okay? So I can start from 0 symmetricity or symmetricity equal to 1, and I just monitor how it changes along the learning process. The learning rule does not preserve symmetry because of the margin. And what you observe is that essentially they go to the same finite value. So it forgets about symmetry. Okay? And then here's another example, which is if we consider a diagonal term which is 0, then, okay, we can consider a learning rule in which we update the JJs in such a way that they preserve symmetry. So we can take a symmetric network and then update it with a local rule that preserves symmetries, like, say, like the Hebb rule for the Hoffman model. This is like in equilibrium propagation. And if you do this, if there's no manifold, the performance are horrible. On the other hand, if there is the manifold, the performance are very good, and essentially they're independent on the fact that there's symmetry or not. So the final message is symmetry doesn't count. Okay. And now, of course, this can be extended to multi-layer networks and to more complicated architectures. Now we have students much younger than you, the second year of the bachelor, that are doing simulations on this, on more complicated architectures, on sparse encoding. Suppose you have just neurons that can take value 0 or 1 in this context, and you force the system to be sparse. So to have only few ones and most of the others that are zeros. Then you have sparse representation, which could be amenable of kind of interesting interpretation from a geometrical perspective, and they are close to much closer to biological reality. And then we hope to use this for finding an algorithm for spiking networks, because this is what spiking networks are just, I mean, sparse encoding just, it's an effective way of describing the behavior of a spiking network. And so if you can find a learning algorithm that doesn't rely on any gradient, so you don't have to do gradient backpropagation through time of a spiking device, but just depends on the state reached by the network, that's kind of interesting. And then there are many, many other projects. And that's it. Okay, so this is the, and essentially the conclusion is that the existence of these connected regions allows convergence, and and allows also learning to set in, thanks to the stability and connectivity of this of the fixed points. And we know how to induce them. So we know how to create them. For instance, you can imagine to create a convolutional neural network just by taking your picture, you projected it in many networks, and then you put couplings between neighboring networks, just to represent the locality. So you can, sorry, a bit fast, but you can easily imagine a convolutional type of network that implements this kind of dynamics. And so you could just learn it, train it without GPUs, hopefully. But the idea is you can train it without any gradient. Whether this is curious or relevant